Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into reinforcement learning, a fascinating field. We'll be exploring a concise yet comprehensive overview, focusing on problem-solution pairs that illuminate the core concepts. Ready to get started?
Absolutely. I'm particularly interested in the evolution of techniques, from simpler methods like value iteration to the more sophisticated approaches like PPO. Let's hear it.
Great. So, we begin with the fundamental problem, finding the optimal value vector and policy in a Markov decision process, MDP. The initial solution is linear programming, but its computational cost is a major drawback. That's where value iteration comes in, repeatedly applying Bellman updates until convergence. Simple, elegant, and effective, but it needs the full MDP model.
I see. So value iteration relies on having complete knowledge of the MDP. What happens when we don't have that luxury?
Exactly. That's where Monte Carlo methods step in. Since we lack complete knowledge, we sample trajectories and estimate average returns. First visit and every visit Monte Carlo prediction offer different approaches to this estimation. But, there's a catch. Pure Monte Carlo methods have high variance and require waiting for episode completion.
Right, high variance. So how do we address that? Is that where temporal difference, TD, learning comes in?
Precisely. TD0 uses bootstrapping. Instead of the full trajectory return, it uses the immediate reward plus the estimated value of the next state. This reduces variance significantly. And from there, we can extend TD to control algorithms like SARSA and Q-learning. Q-learning, in particular, is quite powerful because it aims for optimal values, not just values consistent with the current policy.
Interesting. So Q-learning is more ambitious, aiming for optimality. But doesn't that introduce bias?
You're spot on. That's why double Q-learning exists. It uses two Q-value estimates to mitigate the positive bias inherent in Q-learning. It's a clever solution to a subtle problem.
And what about the limitations of tabular methods? I mean, what if we have a huge state space?
That's a crucial point. The number of states can easily explode, making tabular methods impractical. That's where function approximation comes in, typically using neural networks. We then need to adapt our algorithms to work with these approximations. Semigradient TD0 and SARSA are examples of this adaptation.
So we move from tables to neural networks. That's a significant leap. And what about off-policy learning? How do we handle that with function approximation?
Off-policy learning with function approximation is notoriously unstable. Techniques like experience replay, separate target networks, double DQN, dueling networks, and n-step rewards are all employed to stabilize training. It's a complex area with ongoing research.
Fascinating. And then there's the shift towards direct policy optimization. Methods like reinforce and its variants, actor-critic methods, TRPO, and finally PPO. It seems like a progression towards more robust and efficient solutions.
Exactly. Policy gradient methods directly optimize the policy parameters, often using techniques like baselines, generalized advantage estimation, GAE, and trust regions to improve stability and efficiency. PPO, in particular, is a very popular and effective algorithm that balances exploration and exploitation cleverly. It's a remarkable journey from simple value iteration to the sophisticated algorithms we see today.
It certainly is. This has been a fantastic overview. Thank you for this clear and insightful explanation.
My pleasure. And thank you for listening to Tech Bytes and News. We hope you enjoyed this deep dive into the world of reinforcement learning. Until next time, goodbye.
Bye-bye.